Hi there viewers, and welcome back to uh, Game Boy and Game Boy Color hacking tutorials, and once again using Pokemon Silver ROM for examples. And today I will show you a little bit of event editing, and after doing that we'll get to basic scripting. So let's just start with what we've got. For example, in let's go to Ecratic City. Yeah. And as you can see, this is what the map looks like. Like I said before, the map data starts here, ends right here, and then we have events for the map. We have warp data, consisting of all the warps, and each warp has its position XU location along with where it leads to. So each warp takes 5 bytes. Then we have signposts, also XU position along with direction byte or function byte, as it's referred to in scripting compendium that I'll be showing next. And it has a script pointer, so it's 5 bytes to location, direction, script byte. And then we would have trigger events, which also have 2 bytes for position, and then some other bytes such as flag number they use, script pointer, and 3 bytes that well, are somehow related to the trigger events, but they should just be 0 zeros for making these events run correctly in the game. And finally we've got people events, which consist of 13 bytes. So 2 bytes for location, then they have a picture number defining what they look like in the map. As you can see, I can only use some picture numbers for this guy here, and these are actually because of we are now editing a map of so-called map bank 4. This is map 9 in map bank 4, and this map bank, it has nothing to do with ROM banks. It is actually it defines properties of maps that belong into this under this category. So it's a category 4, and it has properties such as what the roof tiles look like in the map. So we've got palette bytes and a thing called sprite set. 9 walking sprites, 58, 40, 67, 47, 39, 35, 37, 43, and 244. And then we have 2 standing sprites. So these are sprites that cannot be moved, and here they are: Pokeball and this berry tree. And Chodo map shows it in a false way that we would also have another 12th sprite here after these 2, but this is not part of the map bank sprite set. So we have 9 walking sprites, like seen here, and then we have 2 sprites for only standing. So that's what are the properties of a map bank. So only these sprites shown in this sprite set can be shown in a map using this map bank if the map properties, if under here in the map properties type is set to town, road, or is it this indoor? I'm not sure. But those are related to this type byte used here. So unknown is 00, this is 01, 02, 03, 04, 05, 06, 07. So we have 8 different type bytes from 00 to 07. And if this was indoor map, we could use any sprites. But for instance, we change this to 42, make this map a town map again. The sprites won't show correctly. It will show as a player if we go and check the sprite in the game, unless it belongs to the sprites used in the map bank. But this is what each map bank holds in it. And for each map in each map bank, we have a primary map header and a secondary map header. And the primary map header for this map is in 94508. So let's just open that offset. 94508 was it? Probably yes. Yeah. So as you can see, we've got here 25 and OD4F. These 3 bytes here, 25 OD4F, they define the location of the secondary map header. And that is a 3-byte pointer to that ROM address, because 25 multiplied by 4000 is 94,000, and if we add 4F OD to this and minus 4000, you're as well at the same time you're actually adding FOD to this and getting 94 FOD. So this is a so-called 3-byte pointer to secondary map header. The first byte defining the ROM bank, and these two bytes is the pointer into that ROM address. And here you can actually see that the primary header and the secondary header are in the same ROM bank, but still we have a 3-byte pointer to the secondary header. But yeah, these two O1s here, they are probably used for the tile set and type byte. 0001 is town. Then we have 16, as you can see it's unsigned. 22 is probably the so-called name here. As you can see, exit is here. This is 000102, and this is probably 16. And that simply defines under which where we are shown in the town map. That's what it does. And then we have music byte 44, which is this byte here. And finally we've got 2 bytes. I'm not sure what this one does, but this one is has something to do with the phone call information, whether you can be called from a trainer while being in this map, and it also defines the palette used by this map. So 00 stands for probably that you can be called while you are here, and the palette used by this map is defined by the time of the day. So if this was 01 instead, if this was 01 instead, it would mean that the palette would probably be morning palette all the time. So you can see that kind of bytes used for this byte here too. There's a lot of documentation behind the primary, secondary headers and all that in Scatterdoing, so go and check stuff there instead. I'm not going to explain the basics behind everything because that's just not needed. And for next, let's go to the secondary map header. 94 FOD, somewhere over here, right here. We have 0.5 for border tile. Then we have height of the map, width, 2B for 2B 4455, pointing to the map data AD 544. This is also so-called 3-byte pointer. And in the game we actually don't have things called 3-byte pointers, but we have the processor dealing with these bytes so that the map data is loaded from this ROM address. We only have 2-byte pointers, but the first one is used for defining the ROM bank during a certain method. Next here we've got the ROM bank of event and script data. So they always have to be in the same ROM bank. Then we have 2 bytes defining where the map's script data is located, and 2 bytes defining where the event data starts. And next we have 0.7. This is used for map connection data. So 0.7 defines that this map is connected down, left, and right. As you can see, 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, down, left, and right. And following with, we just have the map connection data to all those 3 directions. And this thing is kind of complicated, and I'm not even sure if I'm going to explain it in any way, but you can find a complicated tutorial by me in Scatterdoing, which really isn't that good, but it covers some of the required information behind editing these map connections between different places. But yeah, let's just go to the event data. So as you can see, this was the ROM bank, and then we have the address or the pointer. So let's just check out where that is. I could also, of course, check it here, but let's just calculate it. And we add 9 EE to this. And it's in 1249 EE. 1249 EE. Here's the event data, and you can see 2 00s here. The event data works so that we point to 2 00s before the actual event data starts. And after those 00s we have 0F, defining how many warps are in that map. And then we have 5 bytes for each warp. And normally if I wanted to check out where the well, it goes so that first we have a number of warps followed by the warp data. Then we have number of trigger events followed by the trigger event data, number of signposts followed by the signpost data, and finally number of events followed with the event data. And that's where the event data ends. But you can see here those warp numbers. Let's just try to check out where the warp 0 is located first. Here. As you can see, warp 0 And here we see that the current event is in 1249 F1, which is right here. So Jodo Maps shows this conveniently and in order that if you check out where the selected number 0 is located, you know that the first one of that group is right there. For instance, in this one we have warps. The first warp is in that offset, and right before it we have the number of warps. And for signposts, let's just check out where the first signpost is. It is this one. It's in 412 4A3E, which is right here. This signpost data. And this first byte is its geolocation. Then we have X location, function byte, or this direction here, and script pointer. 3F45, which is in Jodo map 45 3F. As you can see, these are in other direction here. And this is so-called big Indian form of showing a pointer. And in ROM you write them as Little Indian format. So you write them backwards in the ROM, and the editor here shows them like you'd probably want them to be shown, because this is so much more simple way of showing where the script pointer leads, because you just simply pick those bytes and put them right here. Of course, this 4 here comes from the start of the ROM bank, not this 4. This is the start of the ROM bank. You add the script pointer to this one at minus 4000. Just like we've been doing. But we don't have to rotate the script pointer around because it's already done for us. And that is a Little Indian. This is big Indian format of a pointer, and this here is Little Indian, where the pointer is in another direction. But yeah, what I wanted to say that the first signpost is located in this offset, and before it we have the number of signposts, and before that we have the trigger event data, which is right here. It's only a 1 byte long because it's 00 for defining there are no trigger events in this map, and signposts data flows straight after this 00. And for people events, let's just look for where we have select person event 0. Here it's in 12 4A67, which is in this offset here. And 1 byte ahead of it, we've got the number of people events, which is 06. So we have 6 people here. And the first people event is here. And you can see 2F is its picture number. Then we have XU position, or in ROM we've got UX position actually. UX. Phase type, movement value, time type and time value. This probably used for palette and byte. Those are both values are 0, making 0 0, and site range is actually 1 byte value, which is 0 0. After it, we also have the script pointer, which here is in big Indian format, and here we have it in Little Indian OB45. And flag index and flag bit are FF. And these stand for making this person event be shown. FF if these two are FF, the person event is shown all the time if it's not made hidden for a little while. But even so, if it's made hidden during a script, you go away from the map, you come back to the map again, the person event is still there. But if these are something else, a certain bit in RAM is activated. And just like I said before, it was that RAM area here, flags. So when a certain person event is made hidden, a bit is written here and is set to 1. Because here these are bytes. Bytes can have all the values between 0, 0 and FF. But when we have bits, bits can only have values of 0 and 1. So these two, they are sort of a pointer to a bit. They're defining what bit this person event uses. And when the map is loaded, if that bit is set to 0, the person event is shown. And if that bit is set to 1, the person event is not shown. It's kind of complicated at first, but you'll get used to it. So for instance, rival's flag index here is BD and flag bit is 6. And when the bit that these two bytes refer to is 1, this person is hidden. When that bit is set to 0, this person event is shown. And 1 is written to that byte probably during the script you meet with him in Cherry Grove City, because then he is not here anymore. That's how flags work, and I'll be explaining more of these later, but that's just some preliminary explanation behind them. But anyway, let's just open a document called Scripting Compendium. You can see how to access it. Write this, or search for this document and you should find a site. And I'll link a certain video to this one, which you can watch, where I explain all the definitions behind the scripting commands. So yeah, go and watch that one. It's very useful. And along with that one, I'll also link another video to this one related to explaining the script of a certain event in Elm's lab and what happens in it. But yeah, this is a very useful document because it covers everything you need to know related to scripting. And today I'll be explaining how to create your own scripts, and we'll be using this document as a help. And I'll take a little pause break before that, and I'll be back. Okay, I'm back. And well, before watching this part of this video, I would actually like you to view those 2 videos linked to this one instead before doing this, because well, I'm not going to explain everything step by step, although I'll try to keep things as simple as possible, but still. So for example, let's just go and do something about this fat guy that we've got here. So his script leads to 12009B, and it's right here. His script data starts in this offset with byte 51. So if we didn't have a script editor, we would just follow his script data with a hex editor and checking what it does. If we wanted to see what his script does. But well, I'll show that quickly. So his script data starts with 51, and this is text1 code here. And you can see what it does here. And as explained afterwards, there is no other script interpreted. So his script data is 3 bytes long. It consists of 51 and a 2-byte text pointer. So script data is 51, 7E, 42, and that's it. It contains nothing else. And if you open it with a tool called pksv, which you should really install in your computer, it can show you what it really does. And here too, the pointer is in big Indian format, like here. 427E leading to 12027E. And in ROM we've got 7E42. Here we got 427E. In different order. But anyway, let's just do something about this guy. And make him do different things. And like I've explained before, there's always blank ROM space in the end of a ROM bank. So let's just go looking for where we could find some. And apparently we've got blank space here. And this byte here is probably already used, but let's just leave a couple of bytes. A couple of zeros here before writing our own data, and we could, for example, write here. And the offset we're going to write to is 1225A2. So we've got to make this guy point to that offset. And well, the two last digits have to be A2, because like you can see here, 9B leading to 9B. And the first 2 digits have to be so that when you subtract 40 from them, you'll get this 25. So 65A2 leads to 1225A2. So let's just make this guy script pointer lead to that offset first. Okay. And now we have made this change, we've got to reload the ROM, because if we did write our script data there now, it would remove the change of changing this guy's script pointer, because it was written somewhere close to this ROM address just right now. And for starting out, we could write the script with a hex editor, but pksv is really a much better tool for that. And if we decompile the script now, it will show off like this: 2 calls and 0x0 following it. And this is because, well, scripting command 00 is a call command. 2 by the pointer points to script. When pointer script ends, return to old script. And we've got 3 zeros for each call, for each command. 00 followed by script pointer, which happens to be 2 zeros. and this here is the same as to call 0x0000. This is what this command is. But let's just write if I can use this tool to do that. I would like to write 90 here, but well, if I can, that is. What the heck? I haven't really used this either doing anything, so it's just because of well, you won't be able to see things clearly if I use a Goldfinger, so I'm using this one. For some reason I can't write here. Not sure what it's about. Well, anyway, I'll just write that back with Goldfinger and, well, open the ROM again then. So we go to 122582, write 90 here, and we're done. And after this, Johto map will leave this warning message that the ROM has been loaded or modified after a ROM has been modified by other program. So we should reload this ROM before doing any changes, because that way we would be removing that change done with Goldfinger. But so I just wrote 90 in this address, leading this script to end, because 90 is return code 2, which is used to end most scripts, and these most scripts are all the scripts loaded by trigger events and people events. So you end the script data by writing 90 here. So if we now talk to this person, we would see nothing happening, because nothing expect a script ending command is executed when you talk to this person. But if we, for example, wanted to make it show so that this guy would talk to you and give you, for instance, a berry for report to talking to him, we would first, well, normally before doing anything you wanna plan it out beforehand. So what do we have to do? We have to make this guy, we want him to face us, and then we have to load the font, because like explained in that the part where I explain this compendium, which is linked to this one, font replaces the moving sprites in video RAM, and when moving sprites are loaded, text shouldn't be displayed. So we have to load font before being able to display text. And then we have to make him say something, for instance, hey, take this berry. And next we have to make the script execute a command for making us receive a berry. Next we have to load moving sprites in the ROM and end the script. And this is pretty much what you have to do to make this guy give us a berry. So when you program, you've got to think of things in phases. Here we have to think of what has to happen in the script. First he has to phase us, then font has to be loaded, then he has to say us something, give us the berry, load moving sprites, and then end the script. So let's make him do that. And for phasing, we would have to write 6a in the ROM, and that is a command called phase player with pksv. And for easy comparison, for easily figuring out what command refers to which byte, you can use document written in scheduling, or simply comparing your own script to in-game scripts that use these kind of commands. For instance, you can easily find scripts where you are given an item. For instance, the item finder script in ecruity.xd. So you could, when first writing something like that, you could compare it to what you're trying to do. And next we have the load font. Well, that can be achieved with load font command, which is 47 here. And it also opens a text box. And next we make the person say us something. This can be achieved with a write text command, and followed by it we have a 2-byte parameter, which is the text pointer to the text data. And our script data is in this address, so we probably want to make the text data somewhere close to it. And let's for example put that in, put a pointer to be like this, and that refers to ROM address 1225co. So we've got here we've got plenty of space between these two addresses. Actually we've got 30 bytes, or 0x1e bytes between those two addresses. And next we give player a berry with a give item command. And here it's somewhere close here. Give item code is 1f. Gives item number amount times. So we have 2 bytes for this. For this as parameters, and they have to be a item number and amount. And one AD is used for berry. So you can find it in that guide I linked you earlier. Here, berry is AD. That's the item number for it. So we want to make him give us item AD 0x1, and as you can see we have this gives feedback part here. So if 01, then it's okay. If 00, bag is full. And this here means that I'll probably also explain that in the part linked to this one, but well, a certain byte is written in the RAM, and specifically RAM address D173 here, and we can compare that with the RAM check commands 06 to OB, and well, RAM is 00 if bag is full. So next we have to check whether bag is full, because the item number is given to you only if item number should be given to you only if bag is not full. So we use for example, we use command if false, which stands for 08. When RAM is 00, go to certain address. Let's put this one to IB8. So you're given an item if your bag is not full. This is used for that. Give item. Next we check whether bag is if bag is full. So when RAM is 0, if bag is full, go to this address. And if bag is not full, well, the item is not added to your inventory here just yet. It's added after a check like this one, which follows that give item command. So the command works that way. It doesn't require this check, but it's advised that you have the check after command. And now the person event should tell us, hey, take a berry, give us the berry, and if our inventory is full, it will go. The script will start interpreting after the pointer in this ROM address. So let's copy this thing here and change it to B8. So now this thing here is activated. If we don't have room in our pocket, this thing is activated. And we probably want to make the guy tell us something that, hey, you don't have room in your pocket. And then the script will end. And we do this by closing text box, loading moving sprites, or using end command. Just like we pointed out here, gives player berry, loads moving sprites into RAM, and ends the script. And here I probably want to do the same thing. Close text, load moving sprites, and end. So now this guy's script is like he faces us, loads font, says, hey, take a berry, gives us a berry, and if our inventory is full, it goes to this offset saying, hey, you don't have room in your pocket for the berry. Close text, load moving sprites, and ends the script. And this thing occurs every time you talk to this person again. So you can get an infinite amount of berries if this script works like this. And let's just check it out in the ROM what it looks like. By clicking compile here, you can see here that E number of bytes was written starting at this ROM address, and 6 bytes was written here. And that is 6 because this takes 3 bytes, 4, all in all 4 bytes, 5 bytes, and 6 bytes. And this takes E because 1, 2, 3, 4, 5, 6, 7, 8, 9 A, B, C, D, and E bytes. And that's how it works. But yeah, now we have written that script in that ROM address. So let's just check out how it works in the game. Talk to the person. Well, of course it won't work because we haven't written text data yet. So we have to do that before. But I'll just quickly write the text data with Goldfinger. You can do that too because, well, you know how to edit text. We load the table file, go to the ROM address. So text data, the first text data starts in 1225C0 by making the text pointer lead to byte 00, and then the person should tell us, hey, take a berry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And what I counted there was how many bytes or letters we have in this row. And you can have at maximum 18 letters in a row. And here we have 18, and that is okay. And the next text data should start in this ROM address, which tells us he could, for example, say that your item pocket is full. And now I had to write a line break command here. The first line break command is always 4F. And you can check out how they work by modifying existing text or checking existing text. But now let's decompile the script. Sorry. And you can see that the script editor has already loaded the data inside the ROM, what we wrote there. So this is what it looks like right now. And if we check that script now, talk to the person event, he said, hey, take berry, and a berry was added to our inventory. Hey, take berry. Another berry was added to our inventory. And, well, if you check out the RAM map, you can see that the items are stored here in D5 B7. So let's open Memory Viewer and go to D5 B7. This first byte is 01, telling how many items we have in our bag. And item number 1 is AD, which is berry, and we've got 2 of them. And the list ends with FF, telling cancel. So if this FF wasn't here, we could see this kind of stuff ahead. And if we wanted to, for example, have another item, let's say we have item number 0B, and we've got 4 of them. Put FF here, the bag will look like this one. We've got 4 ice heals. And here we can't access the cancel now. And this is because of total item count being 0, 1. So when we only had berry in our inventory, we could access the cancel. Because we can access inventory slot number of items plus 1. Now we can access inventory slot 2 because that is 9, 0, 1 plus 1. But this has to be 0, 2, and then we can access cancel 2. And if it would be 0, 3, we could access a position after cancel, where we don't have anything. But yeah, let's just let this say like this one for now. And you can see that we can have at maximum 20 items in our bag, and that is 14 in hex. So let's write 14 here, and this is the inventory we got here. Of course, we would have to fill the items in this list to make it look good in the game, but we've got, now the game thinks that we've got a full item pocket. And if we talk to this guy now, well, oh yeah, of course, he gives us a berry because we have room for berries. We don't have 99 berries yet. But if we've got here 99 berries now, and try talking to him, he shouldn't give us a berry anymore. Your item pocket is full. That's what happens. We have used all of the inventory, all of the 20 inventory slots, and we've got the maximum amount of berries, 99 berries, in our item num. Item 1 where we could store the given berry. So now we don't have room for it. And you can see that the text data doesn't look quite right. The next part starts right after the first one. But at least we are not given a berry anymore, because we don't have room for it, and that is good. Because if we were given a berry, it would be filled into after the item's end of list, filling stuff in key item count. And that's not good, because the next one will be put into position defined by this byte, total item count. And if we don't have the given item yet, or we don't have room for it, it would be stored in the next possible position, which would then be after item number 20. And the game is programmed that we can't store there anymore because, well, the game is programmed that way, but we do have to give it information that we don't have room for the berry. So, well, it works like this. So we give it the player berry, and then we use a rum check for checking whether there is room for the berry. And that is defined by some code using this byte here, and looking whether that item is already obtained, and if it is, do we have 99 of them or not? Or 99 or more of them, because we could also have like 783 of them, which would look like this in the inventory, because we have more than the maximum amount. But yeah, that's how it goes. So now this thing here works, but as you can see, we have a bug in this script here. We should fix that thing, and that can be fixed with a command keeping the text box opened. So right here we want to use keep text open, which here is command 53, I think, 54, keep text box open code. And that way the two messages will be separated, and not the second one won't be run before the player presses a key between those two. So, and that's obviously what we want to achieve. So right now, if we talk to this guy, hey, take berry. Okay, we were given a berry. Yeah, because I saved so that we don't have room for them. But, well, let's just take this berry here out too. And now the inventory looks like we don't have anything. And put 40 in here, telling that we don't have space in the inventory for any more items, because we can have 20 items at most, and now we do have 20. So he should say this should work now. As you can see, we've got this arrow here, which comes from keep text open code, and it works. We're not given a berry. He faces us, tells this thing, and well, the script ends. So we just achieved all we wanted to achieve with a simple code. Of course, there are a little bit of nitpicks you have to notice to put this keep text open here, and remember to use this rum check, because if you don't, he will give us a berry even if we don't have room in our inventory for the berry. And now obviously we can have as many berries as we like, because if we store our berries in a PC, come to talk to this person again, with not having our item pocket full, he will start giving us berries all over and over again. And this can be prevented with using bit numbers, which I'll be explaining. Yeah, I'll be explaining those next time, along with more stuff related to scripting. So